Welcome back, students. Today we are going to get into our new unit. Eventually this is going to lead us into quadratics. So here is a quadratic equation. I know it's a quadratic equation because it's in order, and when I look at my first term, I see the exponent of 2. Okay, so this is a quadratic equation. So if I were to try to solve this quadratic equation, to solve for a variable means to get that variable by itself, I would first undo the plus 48 by subtracting 48 on both sides, and this would get me to 3x squared is equal to negative 48. Then I would undo my multiplication by dividing both sides by 3, and I would get x squared is equal to negative 16. And then finally, I want x. I don't want x squared. So to undo that exponent, I do the opposite. So the opposite of squaring is to square root. So I would square root both sides. And this is going to give me x is equal to, I can either have the positive or the negative square root of negative 16. So then if I type this into a calculator, it depends on which calculator you use. If you use a handheld calculator, it's going to say error. And if I were to type this into Desmos, it is going to tell me undefined. Okay, so this right here, when we would have solved these, when you solved these back in Algebra 1, you would have put down an answer of something like no real solution. Okay, we didn't say that there wasn't a solution. We put in this keyword right here of real solution because there is a solution. It's just not working with any number that you have ever seen before. So that takes us into what are called imaginary numbers. Okay, so there's another set of numbers out there that you probably never even knew existed. Okay, so you're used to working with the real numbers 1, 2, 3, 4, or even 0, -1, -2, -3, or fractions or decimals. Okay, those numbers, those are your real numbers. Okay, now we're going to work with what are called imaginary numbers. And the definition of a pure imaginary number, okay, is going to be if you have the square root of a negative value. Okay, in the past, like I said, it would tell us error undefined, but this is now going to be rewritten like this. The square root of negative b is going to be rewritten as the square root of -1 times the square root of b. And by definition, I is the square root of -1. So the imaginary number I is the square root of -1. So I'm going to replace that right here, and this would be the square root of b. So going back up here, what I could have done with this problem is I could separate it to be the positive or negative square root of -1 times the square root of positive 16, which would give me x is equal to positive or negative I square root of 16, which is x is equal to positive or negative, and then the square root of 16 is 4, so this would be 4i. So final answer right here. All right, so again, by definition, I is the square root of -1. So anytime we come up with the square root of a negative, we're no longer going to leave it like that. Instead, we're going to break it down like something like this. Okay, we're going to take out the square root of -1 times the square root of whatever remains, and the square root of -1 will always transform into I. Okay, but sometimes we don't just have I, sometimes we'll have patterns and powers of I. So if we have I squared, remember I squared means that we could write that as I times I. Well, that would be the square root of -1 times the square root of -1, which we could rewrite as the square root of -1 squared. And square rooting and squaring are inverse operations. They cancel each other out, which means that we'd be left with -1. Okay, so that's what's really kind of amazing about these imaginary numbers is the fact that you have your imaginary number I, which is the square root of -1, but then if you take I and square it, it actually gives you the real number of I, or it gives you the real number of -1, sorry. And so then if we have I to the third power, we could rewrite that as I times I squared. And we just said that I squared is -1. So this is negative 1 times I, which is negative I. If we have I to the 4th power, we could rewrite that as I squared times I squared. And I squared is negative 1. So this is negative 1 times negative 1, which actually gives us another real number of positive 1. So if we have I to an odd exponent, okay, we're going to be working with imaginary numbers, but if we take the imaginary number I and raise it to an even exponent, it actually takes us back to the real numbers. All right, so I to the 5th could be rewritten as I to the 1st times I to the 4th. There are more than one way. I think this will probably be the easiest. So if we rewrite this as I times I to the 4th, well, this is going to be I times 1, which just gives us I again. If we have I to the 6th, we could rewrite that as I squared times I to the 4th, which would be negative 1 times 1, which is negative 1. If we have I to the 7th, we could rewrite that as I to the 3rd times I to the 4th, which would be negative I times 1, which is just negative I. And if we have I to the 8th, we could rewrite that as I to the 4th times I to the 4th, which is 1 times 1, which gives us 1. If we have I to the 9th, we could rewrite that as I to the 5th times I to the 4th, which we know I to the 5th we did up here is I. We know that I to the 4th is 1, which gives us I. We could rewrite I to the 10th as I to the, I don't know which one we want to do. We could rewrite this as I to the 2nd times I to the 8th. Sure, let's do this one. And I to the 2nd we know is negative 1. We know that I to the 8th is 1, which gives us negative 1. Hopefully we see the pattern. There's a reason why I wrote them out as a table format in these columns. Everything in this column reduces to I. Everything in this column reduces to negative 1. Everything in this column reduces to negative I. And everything in this column reduces to 1. So you can either memorize those. Okay, I to the 1st is I to the 2nd is negative 1, I to the 3rd is negative I, and I to the 4th is positive 1. And then keep figuring out kind of a recursive definition. Okay, where do I land if I keep counting by 4s? Where is that going to land? Or you could simplify it doing this way. All right, so I to the 31st, if you wanted to, you could continue with your pattern. So here would be 12, and then 13, 14, 15, 16, back here to 17, 18, 19, 20, then 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so we know that this is going to reduce down to be negative I, because when I counted, it didn't take me that long to figure out where it fell in the pattern. Okay, but here is the other way. Okay, this is kind of using some modular arithmetic ideas if you ever get to study modular arithmetic. So we have this exponent of 31. Okay, so 31 is what our exponent is. We know that there are 4 possibilities for what it could simplify down to be. So we're going to take 31 and divide it by 4. 7 goes into 30, or 4 goes into 31 7 times without going over, and that's going to give us 28. And that means that we are 3 away from reaching the 31. So what this remainder tells us is that we have I to the 3rd power, which reduces to negative I. So there would be our final answer. So using this concept, again, this is kind of modular arithmetic is sometimes called remainder math for a reason, because what we care about is the remainder. So if we try to figure out what's the remainder of 25 divided by 4, this is going to give us 6, which is 24, with a remainder of 1, which means that this is I to the 1st power, which is just I. So if we have I to the 66th, we could take 66 divided by 4, and that would give us a 1 here. 1 times 4 is 4. That's going to give us a 2, bring down the 6. 4 goes into 26 6 times, and that gives us 24, remainder 2. All right, so because we're 2 away, that means that's going to give us I to the second power, which is a negative 1. All right, so now let's use our definition of I in order to simplify with some of these values. So if we have the square root of negative 81, type that into a calculator, it's not going to be able to do it for you. Desmos won't be able to do it for you. But we can reduce this after all if we use the fact that I is the square root of negative 1. So we can rewrite this as the square root of negative 1 times the square root of positive 81. And the square root of negative 1 is I. The square root of 81 is 9. And I times 9, even though I is a number, not a variable, we kind of treat it like one, and we'll always write it after the number. So this would reduce down to positive 9I because we wanted to take the positive square root of negative 81. So this one wants us to take the positive square root of negative 32, y to the third power. So I'm going to rewrite this as the square root of negative 1 times the square root of 32 times the square root of y to the third power. So by definition, I know that the square root of negative 1 is I. The square root of 32, I could rewrite that as being the square root. 32 is 2 times 2, that's 4, times 2, that's 8, times 2 is 16, times 2 again, that's 32. And y to the third, I could rewrite that as y times y times y. So taking the square root means I'm looking for groups of 2. So here are 2 2's, here are 2 2's. We have a remainder of 2 left here. So that means that 2 2's come to the outside. 2 times 2 is going to give us 4. Here we have 2 y's. We actually have 3, but it takes a pair in order to take it out because we're doing square roots. So y squared, the square root of that cancels. It gives us just y. So we're going to take a y to the outside, and this is going to give us 4y. We already had an I on the outside, and then what's left under our radicals? We have a 2, and we have a y. All right, this next example, we have 3I times 2I, which 3 times 2 is going to give us 6. I times I is I squared. But by definition, we know that I squared is the same thing as negative 1. So this is going to give us 6 times negative 1, which is going to give us negative 6. So we had imaginary numbers, but when we multiplied those two imaginary numbers together, we actually got a real number. All right, this next example for simplifying, if we have the square root of negative 12 times the square root of negative 2, first I'm going to break down the square root of negative 12, and that's going to be the square root of negative 1 times the square root of 12, I can rewrite as 2 times 2 times 3, times the square root of negative 2 would be the square root of negative 1 times the square root of 2. I know that my square root of negative 1 is I. I also know that square root of 2 times 3, since I have 2 2's, that means that a 2 could come to the outside. And then I have the square root of 3 times, again, by definition, the square root of negative 1 is I, and then I have the square root of 2. So now I'm going to take my parts that I have outside and multiply those together. So 2I times I is 2I squared. Square root of 3 times square root of 2 is the square root of 6. And then, by definition, I squared is negative 1. So negative 1 times 2 is negative 2 square root of 6. Final answer. Again, started off with some imaginary numbers. And since I multiplied them together, I got a power that was even for I, which meant it took me to the real number system. I know this is going to take a lot to get used to. I remember when I was first taught about imaginary numbers in Algebra 2, it kind of really just blew my mind. So it's going to take a little bit for you to comprehend it. As far as applications for it goes, I've heard that electrical engineers use imaginary numbers when they're working with their circuits. But other than that, pretty much the only way that I know how to use it is just to take problems further So then we can actually come up with some solutions versus in the past we would have had to stop and say no solutions or no real solutions. Okay, let's go ahead and move on. So far we've only worked with imaginary numbers, but sometimes we're going to have what are called complex numbers, which is where they're going to have a real part and an imaginary part. So a complex number can be written in the form of a plus bi, where a, that's just going to represent a number. So that's just going to be the real part. Think of all of the numbers that you've learned before today. Could be any of those. And the bi, well, the b is just going to represent a number, the coefficient, and I is the imaginary part. All right. So, for example, down here, we have examples of complex numbers. So 3 plus 5i is a complex number. We could have 3 minus 5i, that's a complex number. But if we just have the 3, then that's a real number. If we just have the 5i, that's what's called a pure imaginary number. So you have to have the real component and the imaginary component to classify it as a complex number. But just like in our real number system, we can add, we can multiply, we can subtract, we can divide. We can do those operations with complex numbers. Okay, today we're going to start off with doing the adding, the subtracting, and the multiplying, and we're going to leave division to the next day. So adding with your complex numbers is a lot like adding with polynomials. Okay, even though imaginary numbers are not variables, they're kind of treated like them. So we have to combine like terms. We have to combine the like parts. So the real number from this complex number of 3 plus 5i is 3. The real number from over here is 2. So we're adding. So we're going to take 3 plus 2. And then we're going to add the imaginary parts. So that means that we have 5i, and we're going to combine that with the negative 4i. So plus a negative is the same thing as subtracting, so that's why I just put the minus here. So 3 plus 2 is going to give me 5, and then 5i minus 4i would give me 1i. So final answer, these two complex numbers add to be another complex number of 5 plus I, with the real number being 5 and the imaginary part being I. So subtracting, basically the same, just don't forget to distribute. So here we'll take the real part, which is a 4 and a 3. So 4 minus 3 would give me 1. Then we're going to take the imaginary parts and combine those. So negative 6i minus negative, that will change to a plus 7i. So negative 6 plus 7 is going to give me positive 1i. All right, then multiplying and dividing. Whether you FOIL, whether you use a Punnett square, whether you use double distribution, you're going to use the same technique that you do with binomials as you do with your complex numbers. So first thing I'm going to do is I'm going to distribute this 8 into the second complex number, which is 2 minus 3i. And then what I'm going to do is I'm going to take the positive 5i and distribute that to the 2 minus 3i. So this is going to give me 8 times 2 is 16. 8 times negative 3 is negative 24, but there's an I attached to that. And then 5i times 2 is going to give me positive 10i. And then 5i times negative 3i is negative 15i squared. But we're not allowed to write I squared, okay? Because I squared, if you have that even exponent for an I, it takes it to the real numbers. All right, so this is going to be the same thing as, I'll do two things in one step here. I'm going to combine my like terms. These are both imaginary numbers, I to the first power. So this is going to give me 16, and then minus 14i, and then minus 15, but the I squared becomes negative 1. So this is really 16 minus 14i, and then plus 15. So my final answer, take the real numbers, and that's going to give me 31 minus 14i. Let's do another example. These next ones are going to be what are called conjugates of each other, and these are going to be important for our next lesson. But the reason why they are conjugates of each other is because they look like the same complex number. The only difference is the sign in between them, the real part and the imaginary part has changed. So one's a plus, one's a minus. That's the only difference. If that's the case, those are called conjugates of each other, complex conjugates. All right, so I'm going to treat this problem like the last one where I'm going to distribute. I'm going to take 6 times 6 minus 3i. And then I'm going to take positive 3i and multiply that by 6 minus 3i. Double distribution. So 6 times 6 gives me 36. 6 times negative 3i gives me negative 18i. And then I'll take 3i times 6, which is positive 18i. And then 3 times negative 3 is negative 9, and I times I is I squared. So combining my like terms, this is going to give me 36, and then these cancel each other out, and so I'm left with minus 9, but instead of writing I squared, I can convert that to the real number of negative 1. So this gives me 36 plus 9, which gives me the real number of 45. So this is why conjugates are going to be important for us, is because they take us from a complex world back into the real world because it gets rid of all of the imaginary components. All right, this next one, these are not conjugates of each other because they have the same sign in between. But what this means is we're taking 9 minus 7i times 9 minus 7i. We're going to take 9 times 9, and that's going to give us 81. Then we're going to take 9 and multiply that by negative 7i, which will give us negative 63i. Then we'll take negative 7i and multiply that by 9 to also give us negative 63i. And then negative 7 times negative 7 is positive 49. And then I times I is I squared. If you want to write I squared, you can, or hopefully you figured out by now that we never keep I squared. We replace that with a negative 1. So combining like terms, okay, this over here is actually a negative 49. And over here, this is a positive 81. So 81 minus 49 would give me 32. And then negative 63 minus 63 will give me negative 126i. All right, so it looks like we have a little application problem. And it says using with electricity. Like I said before, electrical engineering, this is really the only time that I've heard of complex numbers really being put to use. They don't use the letter I to represent their imaginary numbers. They use the letter J. Okay, but otherwise it works the same way. So it says the impedance in one part of a series circuit is 7 plus 8j ohms, and the impedance in another part of the circuit is 13 minus 4j ohms. Add these complex numbers to find the total impedance in the circuit. All right, so all we're doing is we're taking the two parts and we are adding the complex numbers together. So I'm going to take the imaginary parts, add those together. I'm going to take the real parts and add those together. So 7 plus 13, the real numbers, that's going to give me positive 20. And then 8 plus a negative 4, that's going to give me 8 minus 4, which is positive 4. And then that's the imaginary part. So they use the letter J to represent the imaginary unit. So this is going to give me 20 plus 4J. And then this is representing my total impedance, which is measured in ohms. So final answer. All right, so like I said before, it is a lot to take in, knowing that there is another type of numbers out there, another set of numbers rather than the real numbers that you're used to. It's just something that you're going to have to open your mind to. It is pretty abstract, which is why you haven't been taught it in the past. Your brains are probably just now becoming developed enough to understand the abstract part of what it means to be an imaginary number. All right, but again, the really cool thing about imaginary numbers is if you work with certain imaginary numbers and if you multiply them together, sometimes they take you from the imaginary to the real number system.